So yeah, let's get started. Yeah, today we have Mark Popinchalk from New York, graduate student, and will tell us about Mark will talk about the stellar rotation period. Please.
Yeah, okay, cool. Hi everyone, my name is Mark Popinchalk. I'm not going to stand right in front. I am a graduate student at the Graduate Center at City University of New York, which is a big multi-institutional, institution of New York City. I'm at Hunter College, which is one of the campuses, but I never go there. I'm always at the American Museum of Natural History, which is where my advisor, Jack Faraday, works, and where the Brown Dwarf New York City Research Group is based. And I'm not going to talk about brown dwarfs. I got out of brown dwarfs, talk about stars, but it's great research. Yeah, so let's make sure that's good. Cool. I'm going to not use. Great, cool. So talking about stellar rotation periods, it all starts with this paper in 1972 by Andy Skumanich. And Andy Skumanich looked at three things. These were kind of relationships that other people have been throwing around for a while, but in this relationship, or in this plot, we're looking at age on the x-axis. And so we've got the youngest things over to the left, we move towards the oldest things on the right. And the y-axis is showing three different relationships: the amount of lithium in these stars, the rotational velocity, or how quickly they're spinning, and the calcium emission lines for these stars as well. And so the y-axis is a bunch of different units, but these were all sun-like stars, very few of them, just a few handful of stars. And what Andy realized was that they were all decreasing over time. So the rotation periods were getting longer, the calcium activity was decreasing, the lithium abundance was decreasing as well. And so this they were all decreasing, but also at the same rate. And so this is kind of what's known as a Skumanich relationship in the field. And this was such a consequential paper that there was a conference dedicated to it 50 years later, which I got lucky enough to attend and meet Andy Skumanich himself. And so there he is. And so I'm not going to have a paper that's worth a conference in 50 years, but it was pretty fun to hang out with him. But so this kind of started this field of understanding how old stars are by looking how quickly they spin. And so this started with just a handful of sun-like stars, very small numbers, and the rotation periods came from spectra. But I'm now going to fast forward to kind of today. And so we can see what we do to find rotation periods today is we don't look at spectra, we look at light curves. And we look at how quickly these stars are spinning by looking at measuring their brightness over time and seeing how quickly a star spot, for example, is spinning on the surface as it comes into and out of view. That will change the overall brightness as the dimmer star spot rotates in and out of view. And so from this light curve, we can get an idea of how quickly the star is spinning. And so, like I said, we kind of fast forward to today, where we now have what's called gyrochronology, or the study of an age's star by looking at how quickly it spins. For a range of masses, tens of thousands of rotation periods, and many ages. And I'm not going to make many bold claims, but I am going to make a claim that we are in the golden age of time series photometry. We've got Kepler, we've got TESS, we've got ground-based missions, and all this is enabling a wonderful understanding of gyrochronology for various ages. And so the kind of picture of gyrochronology today, I'm taking this from Jason Curtis's plot. I'm going to show you a lot of rotation period diagrams. So I'm going to go very slowly through this first one, where on the x-axis, we have effective temperature. And so we're effectively moving through mass. And so some of these plots will have effective temperature, some of them will have color, but essentially we're moving from the higher mass stars on the left to the lower mass stars on the right. And on our y-axis is going to be the rotation period. So the quickest rotating stars are going to be at the bottom of the plots, and the slower ones are going to be near the top. And so as we kind of move from top to bottom in these plots, we're also kind of moving through age. So if you look at the kind of first half of this plot, it lines up really nicely because we have the 120 million-year-old Pleiades group in dark blue are all spinning faster than the light blue objects in Praesepe at 670 million years, and NGC 6811, the orange points at 1 billion years. And so this is also kind of the time range, time scales that gyrochronology really works for. About a couple billions of years is to where it's most comfortable. And for like F through to the early K stars, everything works out pretty well. They're all kind of stacking on top of each other very nicely. But my whole talk is not about this regime. It's about where gyrochronology, quote unquote, struggles. And that's kind of a cheeky way of saying it because there's still a lot to learn in these regimes. So one thing you might be noticing is that in the M-dwarf regime over here, things aren't stacking quite nicely. There's this big reservoir of rapidly rotating M's, and certainly the mid to late M's, and we'll talk a lot about that, as well as this kind of waterfall effect. And something else that we're not really talking about is what's going on in the ages younger than 120 million years. I should also point out there's this kind of, well, with the Pleiades, we have this kind of nice shape. By nice shape, I mean this kind of round hump to it. But there's also this string of quickly rotating things down here. We'll see a lot of that for our younger groups as well, as we look at their initial kind of rotation distributions at the start of these clusters' ages. So yes, I'm going to be talking about where things fall off, and I'm going to be talking about 3 projects that I'm involved in. One that looked at M-dwarf rotation periods over time, one that looked at rotation periods as an indication of youth in the Takor Association, and then one that talks about rotation periods to inform formation of large, young, dissolving, moving groups. So to start, the M-dwarf regime, just to make sure we're all on the same footing, these are faint, small stars, much smaller than the sun, between 0.6 and 0.1 solar masses, temperature range around 2000 to 4000 Kelvin. And they are the most common type of stars. And so people who like exoplanets want to try and find planets around them, because then there'd be lots of exoplanets. They're also the longest lived things by orders of magnitude. And so it maybe isn't unreasonable for this kind of age dating technique to start to have some issues for some of the longest lived things in our universe. It's always fun to think about that the first M-dwarf stars that were formed are still alive to this day. The universe hasn't been around long enough. Yes, and so they take part in this part of the color magnitude diagram. The other challenge with M-dwarf interiors is that we're moving from partially convective to wholly convective at some point in the regime. And so not only do we have to think about how these stars are spinning, but if that spinning and the way that angular momentum is lost over time has to do with some kind of coupling between this radiative core and this convective outer layer, it's going to be challenging to have the same kind of rules describe partially convective to objects that are then fully convective as well, where they won't have that interplay. Or maybe that'll help them spin down differently. We don't know. So this happens at around M3 for a given spectral type to kind of base you in the range. And so I want to brief aside talking about a spacecraft that I love, the Kepler spacecraft. It was the big thing when I was in undergrad. It was finding exoplanets. It was such a cool mission. And then, of course, it turned into the K2 mission, and it was nice for me for my one of my first grad student projects to get to use some data from it. It had died or had been officially shut down a few months before I started this project. So this is a little to Kepler. But the K2 mission, as I'm sure, as a reminder, looked along the ecliptic, not for 4 years like the main Kepler mission, but about 80-day campaigns throughout, and it came back to multiple areas, or came back to some certain areas multiple times. And so as part of this first project, I was able to look at this NLSDSS sample that Praesepe Color-Period here compiled of M dwarfs, L dwarfs in the SDSS sample. And so this was a really well calibrated sample for me to begin to pull from. It looks like there's tens of thousands of objects there. There are only about 200 or so that overlapped with K2 that we really wanted to use. And just pointing out that even though K2 had some nasty systematics in this, I'm showing you an example light curve here on the right. Even though it had some nasty systematics because of the difficulty in stabilizing, there are some really cool tools to remove those systematics, such as these Everest light curves. And so just wanted to point those out. And so although we measured a few rotation periods, the main part of the project was really drawing from the literature sample of many other rotation period distributions in the M-dwarf regime to try and look at how they change over time. And so I definitely don't want to read this table, but point you to that if you are interested in learning more in my 2021 paper. And so I want to talk about some of the distributions we saw and like what we can say about M-dwarfs and how they change their rotation period over time. But there's a lot of, I'm going to be talking about these distributions, so I want to use clarify some of the language I'm going to be using. So again, this is a rotation period distribution. We've now got the period on the y-axis in a log scale rather than a linear scale from before. That's just to try and highlight the kind of rapidly rotating ones along with the slower rotating ones. Speaking of slow and rotating, on the far left, we have the slow rotator sequence where objects are kind of converged. They're falling onto this Skumanich relation where they're steadily losing their angular momentum in a very kind of known way. And so, and of a given spectral type, most of the objects are right next to each other. They're all within maybe 10% or so the same period. As we move along to the right, we start to see a kind of spread in a given spectral type of the rotation period till we reach this kind of elbow, where if we kind of imagine the slow rotator sequence continuing out, this is the furthest point where there are some objects on that rotating sequence. Other people call this things, but I call it the elbow. And then there is this kind of reservoir of rapid rotators, mostly in the mid to the ends, where everything is still spinning very quickly. And it looks quite similar to how their kind of initial distribution of rotation periods at young ages. And so to show that, this is a big plot from this paper that goes, there's a lot happening. So let's walk through it very slowly. I'm moving across from age from left to right. So the youngest things over on the left, these are clusters usually clusters. So Upper Sco, Pleiades, Praesepe, and Hyades are the four clusters as we move from left to right, from 10 million years to about 700 million years. And then the last column are field objects. So a mixture of ages, usually at least considered to be about 1 billion years or older. And so these are field objects. Those are what the columns are. The different rows are the period distributions at the top, the H alpha equivalent width in the middle. So this is H alpha is kind of an indicator of magnetic activity for these stars as well. And then the color magnitude position position on the color magnitude diagram is on the bottom. And so zooming in to explain what the colors are, for the way that these objects were color coded is that in the H alpha plot, we've drawn this activity boundary that again came from Praesepe's paper, looking at all those SDSS spectra, or looking at the activity from the spectra. And so what this boundary is kind of defining is that objects above this can be considered active M dwarfs and objects below it are inactive. And so I've color coded the points so that the ones that are above the boundary bear the color of that group. And so it's roughly color coded by age. And then black points are those that are inactive. And so if we kind of zoom in now, so that's the whole picture. But if we, bring in to look at kind of the 4 oldest sections. So again, we've got Pleiades, Praesepe, and Hyades, so about 100 million years to 700 million years in the third column, and then field objects in the right. I think that there are some things that kind of stand out. I've drawn a vertical line that is based off of the rotation period column to show this kind of elbow, where I think that you could say maybe this is the furthest point that there is a star that could be considered on that slow rotator sequence. And what we see is that that elbow is kind of moving rightwards. It's moving further and further into the M-dwarf regime over time as we kind of advance through age, assuming that these different clusters are kind of snapshots of M-dwarf evolution. What's also important to note is that even with the field objects, there are the inactive ones are all usually the slowest rotators as well. And we see those inactive objects are in the slow rotator sequence for the clusters as well. And so, and the rapidly rotating ones in the field objects are all still active too. And so this kind of movement rightwards of this elbow, although not as strong like as a kind of formula or description in like a true gyrochronology, does maybe give some kind of understanding of how these distributions are changing over time. And before I move on from M-dwarfs, I really want to point out some of the other work that's been going on with M-dwarfs. Since I made this paper, Ryan Dungey used ground-based survey to measure rotation periods for a 4 billion-year-old cluster, where M67, which is really exciting. I should point out the reason that, or the reason we don't have more older clusters in these M-dwarfs is because they're faint and they're hard to observe. And so this was a really monumental task by Ryan to basically measure these rotation periods. And you kind of maybe could see that, or it might even be too faint to see where the elbow is for M67, or if there even is an elbow at this age at 4 billion years. And yeah, there might be some questions about the sensitivity of this plot, but I think it's really cool to see it really extend out further into the M's at such an old age. Should also point out that Lucy Liu has done a great work with ZTF, which is another ground-based observing instrument, and so has measured loads and loads of rotation periods and has really probed this kind of gap between those slow rotating and fast rotating M-dwarfs in the field sample. And so that's really exciting work. And Luisa Riebel's work as well, looking at the younger M's and looking at seeing how disks are affecting the kind of early distributions of these M-dwarfs, because it looks like it can pile up some rotation periods at early ages, and then it seems that pile seems to go away. And so looking at these distributions at younger ages as well is really exciting. And so yeah, my kind of conclusion for M-dwarfs, we don't necessarily get a full gyrochronology, but we do get this description of the description of the color period relationship across ages expanding. We're getting new clusters and all the way up to field ages. H alpha equivalent width inactivity is really important for looking at the slow rotator sequence. And this elbow is kind of potentially a useful age indicator for M-dwarfs as well. So we talked about M-dwarfs, and now I want to talk about other young things in the Takor Association, which is a group that I've been looking at. So again, reminding ourselves of this picture of Gyrochronology Today. We talked about the M's, and now we're talking about this area kind of down below, where the youngest groups should be kind of existing, rapidly rotating. And so this is kind of perhaps where stars are just on the main sequence, or maybe even pre-main sequence, depending on their spectral type. And so there is some kind of, I'm showing off, again, Luisa Riebel's work, looking at how M-dwarfs look in these young groups. And while there may be some general trends and some population-wide things, the distribution of their initial angular momentum just kind of like random chance of having a little more angular momentum in this star versus that one is really the more dominating factor. There isn't a set kind of Skumanich style law for them to be following, and they're all generally pretty fast. And so they're not necessarily following, like I said, a Skumanich relation. And so that's kind of what early young clusters look like in general, not just M's. We're now talking about F, G, and K's as well. But most of what I've been talking about is clusters. And so that's not how all the stars are in our galaxy. So here is our galaxy. This is flying in using data visualization from the Museum of Natural History. And I want to kind of drive home the fact that not all stars are in clusters. So as we fly in towards the plane of our galaxy, you see this kind of square that's centered. I think it's like a 50 or 100 parsecs around our sun. I think it's 50 actually. And so what you can already kind of stand out are those clusters over densities of stars in physical space. And so if you're familiar with these, some of them, you can maybe see the Hyades, you can see the Pleiades kind of stand out. But what's not showing up here are stars that are overdense in velocity space that Gaia really pulls out when you start to look at their velocities. And what's going to come on here is how stars that might be distributed across the sky are all related to one another when you look at them in their velocity space. So what should be jumping on any second now are some ellipses showing off these young moving groups. And there are just as many of them as those kind of clusters as you were seeing before. And indeed, some of those clusters are kind of part of these moving groups, but these are spread out across the sky, which makes observing them using telescopes to measure their rotation periods quite challenging. How are you going to be able to look at all the sky at once for long enough to measure their rotation periods? Well, the answer is TESS, which is an all-sky mission. And so TESS is so great because it's moving throughout, it's changing its viewpoint throughout. And so what we can do in these 28-day sectors that it's looking at different areas of the sky is from the full frame images, measure, which are about 30-minute cadence, 28 days at a time. We can get good enough light curves to measure those rotation periods. So this is showing the kind of GUI that we use, and I think you can see those kind of sinusoidal shapes that were in my kind of cartoon example before showing up in real data. And so we're able to flick through sectors and train various either high school students or master's students to look at these light curves by eye and measure these rotation periods. And from that, we can get more distributions. So a lot of distributions. So like I said, TESS is an all-sky object, beautiful little telescope, covers northern hemisphere in one year, southern hemisphere in the other, and back and forth, roughly. And I'm just pointing out some other work. Some Adina Feinstein has some good, did some initial rotation period distributions of a bunch of groups, as well as this plot that I keep showing you of Jason Curtis was defined for a big moving group called Pisces Eridanus. But I am talking about Tucana horologium, which I abbreviate as TA, as many people abbreviate as TA. And so this is a well-studied group. Adam Krauss did a big survey of it and attempted to look at it all across the sky. It's known to be about 40 million years old, and that's from age estimates from lithium, as well as some other methods. And going into it, we already had H alpha equivalent with measurements, as well as other age indicators. And so from this membership group that Adam Krauss used in 2014, pre-Gaia, we added a bunch of Gaia objects as well to it. And so this is kind of like how those stars are distributed across the sky, with as well as how many TESS sectors, how many times TESS essentially has visited that part of the sky. And so while there are some gray points, many of these objects have at least one TESS sector. And so that's all we need to really measure a young rotation period. And so to show you their distributions, I'm showing two ages that kind of bookend either side of it. And so in red is the Pleiades at about 100 million years old, and blue is Upper Sco, which is about 10 million years old. Oh, 125, apologize. And so adding the kind of gray points to represent Takor, there's perhaps maybe too much going on at once, so I'll kind of zoom in on just the Endorf regime versus the higher mass stars. And so in this Endorf regime, I want to point out blue points of Upper Sco are still rotating kind of slowly, actually. They haven't spun down all the way as they condense on and like collapse before they become main sequence stars. And so those blue points exist above Takor, while with Takor, they kind of exist in a similar place to the Pleiades and are kind of full main sequence stars at that point. At the high mass age or high mass limit, with our F, G, and K stars, I think that the early, like the Fs and the Gs, again, I've got spectral type running along the top here. And so if you aren't familiar with Gaia colors, look at the top x-axis instead. The red of Pleiades is kind of mapping out the start of that slow rotator sequence that I've been mentioning a lot. And so those white points in the F, G, and early K, or maybe not quite K, but those gray white points are on that slow rotator sequence at this age already. So again, this is kind of that elbow I just was describing in the M's, perhaps is useful for tens of million years ages through the F, G, and K stars as well. What's my next point? Yes, there's that elbow that I was mentioning. Oh, I have to do a little tangent here because I like talking about rotation period distributions, but I haven't really shown you any light curves. And so I've shown you this cartoon of an example of a light curve with this up and down, nice sinusoidal shape. But if you joined us at pizza lunch today, we were talking a lot about complex rotators instead. Now, these things do not look sinusoidal. And what I was showing you here was a full light curve, that if you phase folded it and put on top of one another, you would get just a simple sinusoid and just like one kind of up and down. And so if you were to phase fold these complex light curves, these complex rotators, you get very different shapes than a simple sinusoid. You get these real peaks and valleys, and these peaks and valleys repeat on the time scale of months, one object maybe all the way up to a year. But you get these really sudden changes in the brightness, which can't be due to just star spots alone. If it was a star spot, it would have to take at least like half the rotation to be able to change. Essentially, it can only affect half of it. And so these are quick, sudden changes, and so it can't be caused just by star spots. And so, like I said, bizarre light curves. These are only happening in young, rapidly spinning, about 1 day Endorfs, and it's unclear what the cause of these things are. Some of the ideas for what they could be, and I point you towards this Max Gunter paper, it would be perhaps creating dust disks that were seen at just the right angle, a spot and some kind of dust ring together could do this, or some co-rotating cloud of dust or gas that is blocking the view. It's going to require some more follow-up to figure out what they are, but there were 6 of them that were known in TESS. And so some of them are more dramatic than others, to be sure, but they were known from TESS cycle 1 observations. And so those unfamiliar with TESS is that it does, like I said, the northern hemisphere, then the southern hemisphere, and then it goes back to the other. And so these were all in the south hemisphere. And so they were viewed in cycle 1, and then essentially 2 years later, it came back to in cycle 3. And one of the things that we looked at is that their shapes really change. Now, it's not quite lined up necessarily in phase because it's hard to know where the phase lines up with 2 years in between. But just in general, hope you can recognize that from the column that says TESS cycle 1 compared to the one in TESS cycle 3, which is 2 years later, none of the shapes, I think, are the same from one column to the other. I should mention, I didn't explain that the different colors in each row is the different orbits of TESS. And so you're seeing about 14 days kind of averaged together in each color. And so maybe like in this top left box, you're seeing, no mouse, great. In the top left, you're seeing about 2 months of data averaged in every 2 weeks. And by the time you look at it 2 years later, it looks, I mean, for that top one, there's still that kind of big dip, but over on this other right object, the shape looks very different indeed. So these were the 6 that were known in Tuckor. We were able to find another 3 objects that we think are complex rotators. And when you look at them 2 years later, one does show a big change, one shows no change at all, and one loses its complexity entirely. And so this effect, whatever it is, comes and goes potentially, and definitely changes a lot over time as well. So I have to kind of talk about these whenever I can, because they're so exciting to me. They're very fascinating. I think looking at them, some kind of spectral analysis at certain phases of the light curve would be really interesting, but there's plenty more of these to be found in these young and dwarfs. But going back to this larger distribution of rotation periods in Tuckor, I kind of want to make the point that although there's interesting features within these distributions, I think the more interesting thing is how easy it is to get this rotation period for these stars. TESS, all TESS data is public and easily available. We looked at TESS along with other indications of youth, and I'm showing H alpha equivalent width here at the top. But if you color code it by the so the bottom panel is log the rotation period by color, and the top panel is H alpha equivalent width by color. I wanted to kind of show off which points didn't have the opposite indication of youth. So the gray points in the logarithm in the rotation period are missing H alpha, while the gray points in the H alpha plot are missing rotation periods. They're an object that we have an H alpha for, but not a rotation period. Just to quickly say that we did this for 4 other indications of youth that we had for Tuckor. Like I said, it was a well-studied object. But my main point is that rotation period seems to be an easier way of getting these as an indication of youth. There were for every indication of youth that we looked at, there were always more kind of gray points, so more objects that we got a rotation period for that were missing, say, an H alpha or a near UV measurement or an X-ray measurement. And so it's easy just to go to TESS and get a rotation period and say, is it young? I'm not going to necessarily be able to say it's a certain age, but you're going to be able to say if it has a sub 10-day rotation period, like Tuckor does, then you're going to be able to say that it is young. And so my main point about looking at these young moving groups is that it is easy to get rotation periods for these groups using TESS. It's not just cheap, it's free, because this data is already there. And by combining Gaia kinematics as well as these rotation periods and other indications of youth, we learn more about these groups than just the sum of their parts. My final quick little thing to talk about is this next project that I've been working on, which is now looking at larger dissolving moving groups. And so we'll do another little animation here, starting at the Earth. And that last animation I showed you was kind of blind, because it showed all those different moving groups, the kind of ellipses that they embodied. And as we fly away from the Earth, we're seeing those ellipses of the moving groups come back on. It was showing you them as separate things and kind of like different entities from one another, but that's not always necessarily the case, where the sun and Earth are moving through this kind of stellar young area of the galaxy. And so while there are lots of these young moving groups, they might be related to one another as well. And as we're flying out, we're seeing that these groups overlap. The ellipses kind of fall on top of each other. And while that's not necessarily a clear indication that they are related to one another, there is the chance that some of these different moving groups could have some shared and come from some shared history, some shared area that they were all formed out of in the past. And so one way to see that is by looking again at their Gaia kinematics. here we're seeing the X position and Y position in the galaxy of a few of these groups. Horologium, which I mentioned for the prior project, those stars distributed quite close to the sun versus IC 2602, which is another moving group, and Theia 92, which is a group that was found using Gaia kinematics, that are further away. And while Theia 92 and IC 2602 seem like they're right on top of each other, while Tucana is kind of separated in physical space, again, if we look at kinematic space, they do kind of tend to fall on top of each other. And so Tucana Horologium are the purple squares, Theia 92 are the red circles, IC 2602 is represented by this black dotted ellipse. And although some of Theia 92 looks more similar to a different moving group called Columba, in the blue ellipse over there, this kind of points to the chance of them, all these different groups, perhaps coming back and forming from one larger group that has been tidally disrupted over their only 40 million years orbiting the galaxy. And so we've already started to look at these rotation periods for these groups as well. And so Takor, that group that I talked a lot about, is in the dark blue, and some of these other groups are shown, these other pastel colors in this plot as well. I don't want to go too deep into this plot, but maybe a quick note is that the Theia 92 group, which I already kind of pointed out, is perhaps two different pieces. You might notice that there's a lot of spread in all of the yellow, light yellow points in Theia 92 as we move throughout color or spectral type in this plot. While I mentioned that Takor had already a lot of observations, that the H alpha measurement being incredibly valuable for looking at this age, that's not necessarily the case to have been as well studied for these groups that have only recently been identified with Gaia. But again, Gaia comes to the rescue, because with Gaia DR3, there's this kind of pseudo H alpha equivalent width that comes out of the low resolution BPRV spectra. And so it's definitely not the best tool. And I'll show up the Takor group as comparison to kind of show what kind of shape we would expect. And the units are slightly different, but already we can kind of see that perhaps it's helping us identify in these orange squares objects that aren't necessarily part of these groups or part of a different group perhaps. And so it's exciting to see another aspect of Gaia that came out of DR3 be useful for these groups. I should also mention that although we're talking about an extended group, we're also talking about an extended research group. At the museum, we have these summer and master students who are going to go on to teach science in high schools around the city, but are able to get a master's through the museum and help us with research over the summer. And so a lot of this work has been helpful thanks to them. And these are some of my high school students, part of the science research and mentoring program. Here they are making their TESS curves. And I mentioned how TESS looks at one hemisphere in 1 year and one hemisphere in another. And so this is one of the TESS light curves that has gone continuously from cycle 3 to cycle 4, because no other object can do that. And so I've got another group of students working on it this year. Yeah, so I think I can leave on my conclusions that end-Earth gyrochronology is challenging, but as we get more rotation periods, it's gonna become easier to understand how these objects evolve. TESS and Gaia make it easy to assess whether an F or an M star is youthful, and you can do so for stars across the sky. And rotation period is just one of a valuable tool to untangle the complexity of star formation history around our sun. Thank you.
Thank you, Mark. And yeah, audience is all online and fine. Feel free to raise your questions.
Using rotation as a direct tracer of you, are there contaminants there as well too that you could speak about?
Yeah, I think yeah, with a caveat, you know, there's always a caveat with them. Let me just put up something like this, for example. So yeah, my first kind of thing I should say is that, like, with what do I mean by youth? I think I would say like hundreds of million years. You can see that we've got three groups up here that are between 10 to 100 million years, and all of them across the spectral type range, perhaps arguably not some of the upper scale objects, but all of them have rotation periods under 10 days. And so with TESS, with just a single sector of 28 days, you're going to get at least 2 to 3 rotations for anything that's under 10 days. And so I would argue that anything that is under that is probably within this age range. And so, yeah, I think that so those things are all going to be young. If you're looking at longer rotation periods, there's a chance that you won't necessarily be able to pick them up with TESS, and also that the star is going to be much older, and so perhaps not have as many star spots at that point. So it really is kind of like young in general. Gyrochronology really works well for FG and K, and so you can get a much better age for that. But for like late Ks and Ms, I think anything kind of like rapidly rotating, especially early Ms, is going to be showing youth. Yeah.
Right, you don't have like type binaries and that.
Right, I see, that's what you mean. Yes, absolutely. So yeah, and I think let me get one. That's a very good point. So binaries are kind of the boogeyman of rotation periods. And so I was showing Euclides, and I pointed it out with Jason's plot as well, but many of these red points in here can be prescribed to binaries. And so that is also going to work. So in Jason's main plot, gosh, he's, for this plot, has done some work cleaning up the binaries in Praesepe and NGC 6811. However, luckily with binaries, you're hopefully having some other tool to be able to assess whether they are binary or not. Like, of course, Gaia is really good with the Rui statistic to be able to say whether the astrometric thick should be a single star or multi-star. And so hopefully you can identify when they are binaries, but yes, that is a chance for something to get spun up.
Yeah.
I have just one more. Sorry. Maybe you covered this already, but for the Rotators and theirs, they have a breakdown as a function of age from the moving group. Do you found those on, for example?
I don't off the top of my head, so I'm very familiar with the ones in Takor, but I believe Luisa Rebel has it in one, I forget if it's the 2016 or probably the 2018 paper has it for a few groups there. Yeah.
I think you mentioned this data, but it's also that they are young, but not, or do they, are they there from maybe year very early age? Are they showing up after this phase? Is there sort of like a sweet spot? Or
yeah, I think that's a very good question. I see Luisa on the call if she wants to chime in. I don't know, but I know that
I didn't hear the question. I didn't hear the question. If you can repeat it. I didn't hear the question. If you can repeat it.
Oh, hear the question, right? The question was how these complex rotators are distributed across age, and so I know that you found some in upper SCO and 1 or 2 perhaps.
Oh yeah, no, they're more common the younger you go, but they don't appear to have infrared excesses. They're all really, really fast rotating M dwarfs, and they are, yeah, they're more common the younger you go, but they do not seem to have disks.
I see. There's no cutoff in youth.
No cutoff in youth. Yeah.
Yeah. Okay. Cool.
Great.
Have you looked at the activity index in Gaia? How many of the start do the Q&A with? I know think that it comes from the high resolution spectrum. Maybe that could be open here?
Yeah, that's a great idea. We've not done that yet. Yeah. Definitely do that for our dissolving moving group.
Can you reverse your process? So right now you're using TESS to confirm. Moving groups, is it simply impossible for the, probably not, I'm assuming it's stupid, but is there a way to sort of like try to attach it to the period with or did a joint analysis rather than a confirmation?
Yeah, so I think that's a great question. And so one of the things that we think about, so like I could have done a better job explaining that with Takor, we started with like 380 objects, and I think we recovered just under 300 rotation periods. And so does that mean that we've had 80 interlopers in there, or just that at some point, if you get unlucky and you're pull onto the star, you're not going to measure a rotation period for that? And so I think that like that could definitely feed into understanding whether a star is part of one of these young groups. But I there is some like just that geometric reason for one, but also like contaminants from nearby stars as well are going to rule out whether you get a rotation period for it. But it's also like it's if I think that would be really exciting. So yeah, I think Ruth Angus has looked at the kind of Kepler sample of rotation periods, and Lucy Liu as well, her grad student, and tried to kind of make gyrochrones out of those rotation periods to look at ages a little bit older than this for like a billion years or so, and try to not necessarily groups, but at least stars that have similar ages through that. That'd be the closest thing I can think of.
Okay, so you kind of like take like millions of rotation periods, millions of velocity data,
Oh,
sort of combine them for a joint analysis.
yeah, I think combining them would be totally doable. Yeah. In fact, so a lot of this work that we do with our membership groups are with Jonathan Gagne in Montreal using Banyan Sigma. And so I think eventually the idea is to put these rotation periods in to add to the kind of probability analysis of memberships. Yeah.
Last question. If not, let's thank Mark again.